Welcome to Section 3.3, that is keyed to Young and Freedman's University Physics on projectile motion. This could be anything from kicking a ball to throwing a baseball to projectile vomiting even. You can use the physics of projectile vomiting. Sorry to make it weird. Anyway, of course, any physics book is going to do this sort of thing. This one just happens to be keyed to one particular physics textbook. Let's get started. Projectile motion. So a projectile is, something that's being cast through the air, and so in general, it's two-dimensional motion. Really, I mean, you could conceive of it in a three-dimensional framework, but that's not important right now, right? So some things that we can kind of throw out there about projectile motion. So there are two dimensions. There's the forward dimension, and then there's the up dimension. Let's call them the x, the forward, horizontal, and y, the vertical dimension. Now, although we haven't really gotten to what's called the Law of Inertia, it's in Chapter 4, I think. Even though we haven't gotten there yet, let me just say this, that a body in motion tends to stay in motion. That if I could go into outer space and throw a baseball, it would continue at the same velocity forever until it ran into something. So the Law of Inertia basically says that the x component of any trajectory is going to remain the same. It's not going to accelerate or decelerate. It's just going to keep going until the ball falls back down to the ground. Now, of course, there is this thing called wind resistance, air resistance, and that sort of thing. So I'm not saying you could accidentally hit your brother, but there are, of course, other ways that something moving forward can stop friction. But in terms of the ideal situation, the perfect situation where there's no air resistance or anything, a body going forward at a particular velocity will continue to go forward at a particular velocity forever, indefinitely. And so that's one thing to keep into effect here, and keep in mind here when we're talking about projectiles. So basically what we're saying here is that the initial x velocity, and that's what this symbol means, v stands for velocity. The 0 means initial, the 0 velocity, dun dun dun. And we're talking here about the x component. So the x initial component of velocity is basically going to be the x component of velocity until the thing hits the ground. And we also would say, therefore, that the x component of acceleration is 0. It's not getting faster, it's not getting slower, it's staying at the same rate going forward. I throw the baseball up into the air, and it's going to continue to move forward at the same velocity as when it left my hand, barring wind resistance, until the ball falls back down to the ground. It's not going to accelerate, it's not going to decelerate, it's going to go at the same velocity. Okay, so that's the x component in a simple way of thinking about it. Now, of course, gravity, it pulls it down. And what's going to determine how long the ball stays in the air is how large a y component of velocity it had, and then, of course, gravity. And so the acceleration, the y component of acceleration with a projectile is negative g, which, of course, is 9.81 meters per second squared. I mean, that's not precise even then. But so, or negative 32 feet per second squared, if you're going to go old school. So the acceleration according to y is negative g, where g is basically whatever gravity is. And of course, gravity does change depending on how high up in the air you go and so forth. But that's not important right now. Okay, now air resistance, as I said, can also drag. That's really the essence of this section. But of course, because this is physics and it's university physics, we can't let go without at least trying to make your head scramble. So let's get into a little trig here. So in this badly photographed diagram, let's get back to it. Okay, so we have this alleged trajectory of the soccer ball or the baseball or whatever you want to say it is, and that v0 is the initial velocity in two dimensions. I've done it with x, y. Again, how you do the framework, it doesn't matter, but this keeps it at least somewhat simple. And then I'm calling the angle between the ground, or where it leaves your hand, which may be a few feet off the ground, or a few meters, maybe a meter off the ground, depending on how tall you are. let's say that the zero, the x0, is whatever horizontal level that ball left your hand. And the angle between that and the trajectory, we're going to call that theta. So hopefully, if you're in a course of university physics, you've had a little bit of trig. It's not hard, really. Trigonometry, these basics aren't that hard. Basically, there's a relationship between the sides of a right triangle. So this is a right triangle, which means that this angle here is 90 degrees. And so there is a relationship that's long been known between the measure of this angle and, say, the measure of this opposite side divided by the hypotenuse, and a relationship between this angle and this adjacent side and the measure of the hypotenuse. We call the sine of theta the ratio of this side divided by this side, and the cosine of theta the measure of this side divided by this side. And cos means cosine, sin doesn't mean to go sin, but it means the sine of that angle. And so if I rearrange the terms, just trust me if this doesn't seem familiar, basically if I multiply the hypotenuse, b0, by the cosine of theta, then I'm going to get the measure of this x component of velocity. And if I multiply the initial velocity times the sine of this angle theta, then I'm going, and by the way, these are fixed and known quantities. They used to have tables in the back of books before calculators. Right now you just type in sine of 45, and the calculator gives you the answer. But they used to have tables in the back of books where you could look up the sine. So the sine of a particular measure or the cosine of a certain measure, those are fixed. And so they're known things. You can plug them into a calculator. So basically all I need to know is the initial velocity and that angle, and I can figure out what the x component of the velocity was and what the y component of the velocity was. Those are the formulas. The initial velocity x component is going to be equal to the original velocity times the cosine of that angle, and the initial velocity y component is going to be the initial velocity times the sine of that angle. Again, you don't have to understand it to use these formula. So now if I go back, because the initial velocity doesn't change, then the x component of the velocity is going to be the same throughout. As I said, the horizontal component is not going to change of the velocity. And we said that it is, in the previous formula, remember, the initial x velocity is the initial velocity times the cosine of theta. And so that's going to be the velocity the whole way through. The whole way through, no matter at what point in time you measure the velocity of that projectile, the x component is going to be the initial velocity times the cosine of the angle at which it was first thrown. Now, we can then take some of the formulas from Chapter 2, that is, some general distance formulas. Basically, it's going to continue at that velocity till the projectile hits the ground. And so remember the formula, that x equals initial x plus velocity times time plus 1/2 acceleration times time squared. That's from the previous chapter. Go back and review it. So basically, the initial distance, we're going to define that as 0. So the x0 disappears. So there we're left with vt plus 1/2 at squared. But we said that the acceleration was 0 horizontally, right? So 0 times 1/2 t squared, that disappears. So all we're left with is that x equals vt for this situation, because we said the initial distance, we're going to define that as 0, and since it has 0 acceleration, that last part disappears, and we're left with x equals vt. And so what is vt? Well, v is v0 cosine theta. So we just substitute that in, and so you can know how far horizontally any projectile, any projectile where air resistance is negligible, you can find out where that projectile is in time horizontally by taking the initial velocity, multiplying it by the cosine of the angle at which it was thrown, and multiply it by the amount of time that's passed by. And so there you have it. Nice little formula for finding the x dimension, or the x measure of a projectile, any projectile. Okay, the y is a little bit more complicated, but not much. Again, let's take that same distance formula and plug in instead of the x's, let's plug in y's. So wherever we're at on the y in the vertical is going to be the initial y, which we're defining as 0, times the initial y component of velocity. Remember what that was? It was v0's sine of theta. We're going to plug that in a second. Plus 1/2 at squared. Oh, remember what a is? It's negative g. So basically we know that the acceleration is negative g because the ground is pulling, gravity is pulling. And we know that, as I said, the initial y component of velocity is v0 times the sine of the angle. Substitute all that in, and then what do we get? We get that if you want to know what the y is at any point in time, all we need to do is we need to multiply the initial velocity times the sine of the initial angle times the time, and then subtract 1/2 gt squared. And that's going to give us whatever the y is. And by solving for t equals, for substituting, or finding y equals 0, we're going to, y equals 0 at t equals 0, but y will equal 0 again when it comes back. This is always going to be a parabola, by the way. A projectile motion is always in a parabola. Parabola, if you know, is a curve. In this case, it's an upside-down curve. And so the second place where y equals 0 is going to be where it comes back down to where it started. Okay, well, finally, if we want to find out how far from the point of origin the ball has, in other words, if you draw a straight line from where it released the hand to where the ball is at any point, it's going to be a simple Pythagorean theorem. If you take the x and the y, at any particular point, that tells you, how far from the origin as a straight line it's gone. And if you want to figure out at what angle from the origin it is, then you're going to just find the inverse tangent of the y component divided by the x component. Again, that's a trigonometric formula. If you go back to that triangle, so the sine was the opposite over the hypotenuse, the cosine was the adjacent over the hypotenuse, the tangent is the opposite over the adjacent. And again, this is a fixed, the tangent of an angle is a fixed quantity that you can plug. You just say, what's the tangent of 45? And it's, it's going to say 1, because that's where the opposite and the adjacent are exactly equal. Okay, well, this has been projectile motion. Go throw something at somebody. No, don't do that. Go throw something and see if it follows mathematically.